Okay, welcome back, everybody. Our next speaker is Vincent Brugidou from the University of Lille, and he's going to talk on a specialization of monomial symmetric functions.
Thank you. Hello, I am going to talk about some properties of a specialization of the symmetric monomial functions. First, I speak about P and R. Let's first recall some notation and definition. For an integer partition, the weight is that and the length is equal to R. We need three usual symmetric functions: the elementary En, the power symmetric function Pn, and m lambda, which is the symmetry size of this monomial. Pnr is defined with Macdonald notation by this sum over lambda verifying these two conditions. Note that Pn1 is equal to Pn. So Pnr generalize Pn. Now we talk about polynomial G, and R. We specialize with that equality. We obtain for P and R the following factorization. An important fact is that the polynomial G and R has positive integer coefficients. This leads us to combinatorics. In fact, the G and R are special cases of polynomial which are enumerator of inversions in forest sequences. Between the G and R, we prove this linear recurrence. We notice that the coefficients of this recurrence belong to this set. The horizontal recurrence allows the calculation of the triangle of G and R line by line from the initial condition. Here is a triangle for n less than or equal to 4. For r equal to 1, we get this factorization for Mn. A natural question is, do we have a similar factorization for any m lambda? The answer is yes, and the factorization is given here. Note that the theorem only states that J lambda has coefficients in Z, while those of J and R belong to N. By taking lambda equal to N, we verify that J lambda generalizes Gn. We have proven two recurrences for G lambda. The first recurrence for r equal to 1 is here. The second recurrence for r different from 1, for r different from 1, is here. its coefficients belong to this set. Notice that its coefficients belong to this set. These recurrences allow to calculate all the J lambda. For example, J321 is given here. Note that all of its coefficients are positive. We think it's no coincidence. Conjecture on J lambda. More generally, we conjecture that the coefficients of J lambda are strictly positive and log concave. Here is the definition of log concave. Many combinatorial sequences are log concave. In particular, the column and rows of Pascal triangle are strictly positive and log concave. Three arguments led us to state the conjectures. First argument is that they are checked for all lambda, J lambda already calculated. My colleague Philippe Bobdard checked the conjectures up to n equal to 37. The second argument is that the coefficients of GNR are strictly positive and log concave. The log concavity is a direct application of the work of U by associating to each GNR a matroid MNR. To define this matroid, we start from the complete graph Kn, and we contract all the edges between R vertices of Kn. Then MNR is a cycle macroid of the contracted graph that we denote thus. Here is an example, the example of the contracted graph for n equal to 5 and r equal to 2. This is the complete graph K5. This and this in red are the R vertices. When we contract the edge between them, we obtain K5/2, the contracted graph. If T is the tooth polynomial of M and R, it follows we deduce this equality, where this sequence is the H vector of the complex matroid of the dual of M and R. The conclusion follows from Hu's theorem on the log concavity of this H vector. The third argument for the conjecture is that they are verified by the last n-1 coefficients of J lambda. Indeed, we have shown that these coefficients are proportional to the first coefficients of the column n-r-1 of Pascal's triangle. Take this polynomial as an example. We have this and this. So the number of coefficients to compare is 5, and the column number is 2. We check that the 5 coefficients here are equal to the 5 coefficients of the column 2, 0, 1, 2, multiplied by a number. How to prove completely the conjecture? One possibility is combinatorial. Basically, it is about finding a mathematical object whose J lambda is an enumerator of a characteristic of this object. This will almost give the first conjecture. More elaborate is to try to reproduce the proof used for G and R, since it will prove both conjectures. This consists of associating to J lambda the matroid whose polynomial verifies this equation. But for any matroid, this polynomial is monic, in contradiction with this G lambda, which cannot be reduced to a monic polynomial since its coefficients are coprime. In conclusion, one could look at another class than that of matroids, and which would also have log concave properties. For example, graded poset interval gridzoids. But maybe I'm venturing too far into fields that for the moment I know little about. Thank you for your attention, and to the conference organizer here for more detail. Thank you very much.